In the previous video, I discussed what I would call traditional Bayesian process tracing, which is the way that's been practiced essentially from Thucydides through the last 20 or 30 years. In this video, I'm going to introduce the most recent version of process tracing, which is formal Bayesian process tracing. And my argument is that formal Bayesian logic is what underlies traditional process tracing. It helps us better understand traditional process tracing. We can still do that traditional process tracing informally, but I think there is some value added to at least trying out some of the more formal aspects of Bayesian logic in process tracing. So that's the agenda here. Let me start off with this cartoon, which illustrates the fundamental difference between Bayesian logic and frequentist logic. If you've taken a course in statistics, it was probably a course in frequentist statistics, and frequentism treats the idea of probability different from Bayesianism. In frequentism, probability represents a sampling procedure. It represents the limit of if you were to sample a population over and over randomly, the limit of estimating something from that population. In Bayesianism, probability represents degrees of belief. What are my relative degrees of belief in alternative explanations or alternative theories? So this first cartoon illustrates this difference. We have two stick figures here. They're trying to figure out if the sun has just exploded. And if the sun explodes, there will be a burst of neutrinos, which will hit the Earth and hit this neutrino detector. But this neutrino detector is a little bit sneaky. It's a little bit duplicitous. It won't always tell us the truth. So what happens inside the neutrino detector is it has two dice. Each one has 6 sides. And it will roll those 2 dice. And if they both come up 6, then it will lie to us. And if they come up any other combination, it will tell us the truth. So these two figures ask the neutrino detector, did the sun just explode? And you can hear the dice rattling around, and it says, yes, the sun just exploded. Now the frequentist says, well, the probability that the neutrino detector is lying to us is just 1 out of 36, because there's only one combination of 2 6s. And so I will assume that it's more likely that it's telling the truth, so I will conclude that the sun has just exploded. And the Bayesian says, do you want to bet? Because for the Bayesian, they do the calculation in a different way. They do it according to their prior degrees of belief. And here, part of their prior information is that the sun has been around for 4 billion years. The probability that the sun just exploded in the last 30 seconds when we talk to the neutrino detector is 30 seconds divided by 4 billion years. That's an extremely, extremely small probability. And compared to 1 out of 36, the idea that the dice might have both come up 6 and the neutrino detector is lying to us, 1 out of 36 is way, way bigger than 30 seconds divided by 4 billion years. So the Bayesian concludes that the neutrino detector is lying, and so they're going to either make some money off the frequentist, or if the sun actually has exploded, they'll never have to actually pay their side of the bet anyway. So the Bayesian comes out ahead no matter how you figure it. So as I said, in frequentism, probability is a function of sampling. Technically, it's the limit of relative frequency in many random trials or samples. And in Bayesianism, probability represents degrees of belief in alternative theories or explanations, and it's based on prior knowledge that we then update with new evidence. Okay, so process tracing can be explained using set theory, which Jim Mahoney has done, or using directed acyclic graphs, and potential outcomes, which David Waldner has done, or it can be done using Bayesianism, as I have done and Tasha Fairfield and Andrew Charman have done. These approaches are all consistent, I would say. They're all rooted in conditional probability. And so I don't see any functional differences among them. Some people may be more comfortable and familiar with set theory. Fewer people probably are familiar with directed acyclic graphs or Bayesianism. But I would say they're all consistent. And I will use Bayesianism to explain the logic of process tracing because I think this is the most worked out version of this logic. Bayesian calculations are driven by our theory-based inductive estimates of priors, our going-in knowledge and guess as to which what's the likelihood that alternative explanations are true, and then driven by available evidence. So the results are only as good as what goes into the calculations. If you don't have a well-informed prior and you don't have strong evidence, you won't be able to reach strong conclusions. If you do have a well-informed prior and you have lots of powerful evidence, and I'll describe in a minute how we know whether evidence is powerful or not, how we assess that, then you'll be able to really strengthen your confidence or weaken your confidence in alternative explanations. So it's only as good as the evidence that goes into it, but Bayesianism provides a consistent, transparent, logical basis for process tracing, and it also relates to the philosophical basis for making choices among explanations or theories and for narrowing intersubjective disagreements. It'll make it clear whether two people disagree on the prior or the likelihood of evidence given the theories or the reading of the evidence itself. Whereas sometimes in process tracing that's not as formal, this remains a little bit mysterious why people disagree on the value of evidence. Okay, so I would say that formal Bayesian logic is the logic of traditional process tracing. It outlines it more clearly, and it shows us that a lot of the traditional insights and arguments about process tracing have a basis in Bayesian logic. But also there's some practices in traditional process tracing the Bayesian logic might improve upon or even challenge. And I think that's one reason we want to pay attention to Bayesian logic. So whether we want to use it just to understand that there is a logical basis for process tracing and to improve our traditional process tracing, or whether we want to use Bayesian logic fully and formally, which I'll show you how to do, that's going to be up to you, but I think it's useful for us either way. So we already have in common everyday usage some ideas of informal Bayesianism. And Stephen Van Evera has written about this. A lot of people are familiar with the idea of a hoop test, that a theory might have to jump through a hoop to still be a possible explanation. So a hoop test is asymmetrical. If the theory survives the hoop test, then it's still a possible explanation, but we don't greatly increase our confidence in the theory. If it fails a hoop test, then we greatly decrease our confidence in the theory. So it's it's asymmetrical in that regard. A smoking gun piece of evidence or smoking gun test is asymmetrical in the opposite direction. If we find a smoking gun in the hand of somebody after we heard a shot and we saw the body fall, that's very powerful evidence that that is the person or that is the proper explanation. But if we don't have smoking gun evidence, or if something fails a smoking gun test, it does not necessarily greatly reduce our belief that there's a probability that that person is the suspect in the murder, right? So a hoop test is asymmetrical. If you fail, it greatly decreases your confidence in the theory. If you pass, it doesn't greatly increase your confidence. A smoking gun test, if you pass, it greatly increases your confidence in that explanation. If you fail, it does not greatly decrease your confidence. A doubly decisive test is powerful in both directions. No matter what the evidence is, it will strongly discriminate between alternative explanations. So Steve Van Evera mentions this is like a bank video camera that catches the face of the bank robber. It tells you it is that person, it is not anybody else. And then finally we have straw in the wind evidence, which is sort of weak evidence. It might slightly tilt you toward one explanation or the other, but it's not very powerful evidence. Now, this is informal language. These are points on a continuum. A smoking gun test, hoop tests, and so on can be more, tighter or looser. This language fits our sort of everyday insights about Bayesianism, but sometimes when we try to do Bayesianism informally, we'll fall into particular characteristic mistakes and certain cognitive biases and so on. So that's one reason it's important to understand some of the formal logic of Bayesianism. So if you do know these basic Bayesian intuitions and you think roughly about alternative explanations and priors and estimates of how likely is evidence under this explanation or that one, you can still get pretty far. But I would say, as I mentioned earlier, informal Bayesianism might lead you to some informal mistakes, and it might be better to use the logic systematically and transparently. So formal Bayesianism is common in many fields, in computer science, in other areas of decision making, but it's fairly recent that it's been applied to process tracing. There's a number of examples where people have gone back to other people's work and analyzed it in formal Bayesian terms, and there's only now starting to be some people and graduate students who are doing formal Bayesian analysis as they're doing their work and gathering their evidence and assessing their evidence. But that's relatively new. We don't have a lot of publications yet using this method. So you may still have a challenge in encountering journal reviewers who are not exposed to this, who haven't read about it, and you may need to explain your methods to those reviewers. But it is becoming, I would say, more and more people are taking interest in it, perhaps trying it out in their own work. And that may give you a leg up if you run into the journal reviewer who does know that this is a sort of cutting edge method that may actually help you get to publication. Okay. So let me give an example of Bayesian logic. And this is kind of the standard textbook example that you'll find and it comes from a medical example, which is a common example that people use. So let's assume that the following information is known and true. That on average, 10 people out of 1,000 people in the population have a certain kind of cancer. And on average, if you test people for that kind of cancer with a specific test, then 8 out of 10 who have cancer will test positive for cancer. But let's also assume that same test has some false positives, that 99 out of every 1,000 people that do not have cancer will still get a positive result on the test. So the question is, if you go to your doctor, you take this test, and it comes back positive, what are the odds that you have cancer, right? And most people guess that the odds are pretty high. In fact, they're still pretty low. They're much higher than they were before you took the test, but they're still pretty low compared to all the possible outcomes. Let's see why that works. So here's kind of an intuitive way to visualize this example. Here we have this big circle, which is the full population of 1,000 people. Here we have the small circle A, that's all the people who have cancer. So that's 1 out of 100, 1%, or 10 out of 1,000, right? And so this circle is 1/100th the size of the big circle, right? So we're just representing percentages by relative size of areas here. And this green circle B is the people who test positive but don't have cancer, right? The green part's minus this doubly shaded part. So I said 99 people will test positive even though they don't have cancer, right? So what we want to know when we test positive is what's the ratio of the true positives versus all of the positives. That will give us the likelihood that we have cancer. So here, that is these 8 people who do have cancer and also test positive, divided by all of the people who test positive, which is the 99 plus the 8. So it's 8 divided by 107, or it's less than 8%, right? So we can just see visually that this doubly shaded region, the true positives, would be a small proportion of all of the positives. This little sliver that's red is the false negatives. Those are the people who, those 2 people out of 1,000 who the test says they're negative, but actually they do have cancer, right? Okay, so this just gives the math for the result as I just gave it, right? Let's look at the bottom line here. 8 people out of 1,000 divided by the 107 people who test positive, and so we get a 7.5% chance that I have cancer if I test positive. Now that's, almost 8 times as much as before I took the test, so it's not good news, but it's 8%. There's a 92% chance I don't have cancer, and so it's not, necessarily terrible news, right? So the challenge here is that when people use their intuitions to do the Bayesian logic, their intuitions often lead them astray. In fact, there are studies where doctors are trained in Bayesian logic because often they're doing diagnostic tests that have a known true positive and false positive rate. And often doctors still get the math wrong. So if you learn nothing else from this, you'll learn to sort of double check your doctor and make sure they're doing the math right when you get test results, and ask them, what's the general incidence of this disease in the population or for people like me, and ask them, what's the true positives and the false positives of this test, right? So that's the intuition. Basically, again, just to show you the picture, it's just saying that, a big proportion of a small number, the doubly shaded region, the 8 out of 10 who have cancer that will test positive, is smaller than it's a small proportion of a bigger number, which is the number of people totally who test positive on the test. So even though about 1 out of 10 people who don't have cancer test positive, since there's a lot of people in the population, 1 out of 10 is a much bigger number than 8/10 of 1%, right? Okay, so in Bayesianism, what we do is we start with our initial information, everything we know from prior experience and research and study, and that informs our initial degrees of belief in alternative explanations. We call this the prior, right? Our going in knowledge. And then we inhabit the world in which a theory is true. We mentally assume that a theory is true, and we ask, how likely is this kind of evidence to take this value if the theory is true? And we'll ask the same question of other theories, right? And this gives us what we call our likelihoods. How likely is the theory? How likely is the evidence if the theory is true? And it's really the relative likelihood of the evidence under these two different imagined theoretical worlds that matters, right? So even if evidence kind of seems pretty likely in terms of one theory, if it's even more likely in terms of the other theory, then finding that evidence favors the second theory, right? So it's the relative likelihood of the evidence given whether the assumption that one theory or another is true that determines the updating, right? So then we go and look at the evidence, we find out what the value is on that evidence, and then we use the conditional probability of the evidence given the theory to work the mathematics to give the likelihood of the theory given our reading of the evidence. And this new updated estimate is called the posterior. So we start with the prior, our going in guess of the likelihood that different theories are true. We establish the likelihood of evidence if this theory is true or if that theory is true. We look at the evidence, and then we come up with the posterior, our updated estimate of the likelihood that different explanations are true, right? So this next slide just shows the Bayes theorem, or one version of Bayes' theorem in the mathematics. Just to walk it through quickly here, and you may want to take some time to look at it if you haven't seen it before. The updated probability that proposition is P is true given evidence K is our prior, our going in guess of the likelihood that P is true, times the likelihood of evidence K if P is true, right? So this is our true positives. You notice that the left-hand side of the denominator is the same as the numerator. This is the true positives. The right-hand side of the denominator is the probability if P is not true times the likelihood of the evidence K being the same value if P is not true. Okay, so in other words, it's the true positives divided by the true positives plus the false positives. So think back to our cancer example. It's the true positives, 8, divided by 8 plus the false positives, 99. So 8 divided by 107. Okay, the rest of this just walks you through the notation. Note that the math is not that complicated. It's just, multiplication, addition, division, subtraction. You can actually go online to this Bayes calculator. If you have the slides, you can hit the link. But if you just Google, here's the, or type it in, here's the website. And you could put in your prior, and you can put in your likelihoods, and it will spit out the updated posterior, right? But the real work here is in estimating the evidence given the nature of your theory, okay? So, okay, got mixed up with my slides here. Okay, so Tasha Fairfield and Andrew Charman have thought of some very interesting ways to pragmatically apply this formal Bayesian logic. And what they do is they use a slightly a mathematically equivalent but rearranged version of Bayes' theorem compared to the one I just gave you, which is called Bayes' odds form theorem. And they use a logarithmic scale of measurement, which may seem more complicated somehow, but actually they make a convincing argument that that simplifies some things. And I'll show you how that works. But just to give you the Bayes rule with the relative odds form, this is again from their work. So what this is saying is the posterior odds, the relative likelihoods of these two explanations or theories being true, so this is our posterior, is equal to the prior odds, that's the relative odds of our prior estimates, times the likelihood ratio, which is the ratio of the likelihoods of the evidence given H1 is true or the likelihood of the evidence given H2 is true. So this is just a mathematical rearrangement of the previous version I gave you. If you read their book, which I hope will be forthcoming soon, I'm speaking now in June 2020, you'll see the derivation of that. You'll see a lot of the math behind that. For now, I'm just going to leave that to your intuition, or maybe if you've seen the math before, you'll understand it. But I'm going to move on to just try to develop your intuition rather than working through all of the math. Okay? So the second intuition here that they draw on is that a lot of human perceptions of light, of hearing, of sound are actually on a logarithmic scale. So the decibel scale is one scale that they use because it's easy for us to think in terms of sounds and how powerful they are. And we'll see that we can translate that into estimates of the weight of evidence on this same logarithmic scale. So on the decibel scale, 10 decibels is a pin drop. That's sort of the lower threshold of human hearing. 30 decibels is a whisper. 60 decibels is a typical conversation. 70 is a noisy restaurant. 80 is an alarm clock, right? So these correspond, when we translate into weights of evidence, to sort of weak evidence at 10 decibels. Somewhat stronger evidence at 30. Pretty good evidence at 60, and very strong, above that, because as a logarithmic scale, these are, much, and 100 decibels would be a kind of a very noisy dance club. That's sort of hearing damage territory, right? Now, the reason that that is useful and actually simplifies things, I mean, you may not have seen or worked on logarithms since your high school math, and you may be a little bit confused at this point, but you can work through the math in their book once you get it. And the reason that that actually simplifies things is that when you turn things into logarithmic scales, then you can simply add the weights of evidence. So this is the logarithmic conversion. And so if we do the weight of evidence of, let's say, we think this evidence favors this hypothesis over that one by, let's say, 30 decibels for this piece of evidence, and maybe it favors the first one by 10 decibels on the second piece of evidence, and maybe by 20 on the third, well, then we can add 30 and 10 and 20, and we'll say that's a total of 60 decibels. So we'll take these three pieces of evidence, and now they favor, whereas the individual ones were sort of a conversation or less, altogether they're sort of, a noisy restaurant or a loud conversation, 60 decibels, right? So since we've converted things into logarithms, we can simply add the weights of evidence if we've estimated the weights of evidence in terms of this decibel scale. Okay, so again, let me just leave that as an intuition, and let me move ahead and give you an example. And we can also put the priors in this logarithmic scale as well. Okay, so but just before we get to the example, this is a very nice summary from Fairfield and Charman's article in Political Analysis in 2017. And it gives you the process for carrying out formal Bayesian assessments of the weight of evidence and how we should use that evidence to update our priors. So first we have to start with mutually exclusive hypotheses. And that's up to us as theorists. Now, we can imagine, let's take a simple example of, there's been a murder that's occurred, And one possibility is that subject A committed the murder. Another is that subject B committed the murder. Another is that A and B worked together to commit the murder. And another is that neither one of them is guilty of the murder, right? And so I've just given you some mutually exclusive hypotheses, right? Now, it's more challenging to think of what would be the evidence that would be consistent with A committing the murder alone, but not consistent with A and B colluding together to commit the murder. That's a tougher question. But in principle, we can divide hypotheses any way we want. We can think that things are working together, just as our suspects may have been working together. We can bring in structural and agent-centered theories and whatever, and we can combine them in whatever ways we want. But ultimately, we want to partition those hypotheses or combinations of factors into mutually exclusive ones. Otherwise, the Bayesian mathematics won't work. And this is one area where I think Bayesianism forces us to be more systematic. A lot of times in traditional process tracing, people are a little bit loose about, how they're combining different factors into different hypotheses. This forces us to be more explicit on that. And once we've partitioned our hypotheses into mutually exclusive ones and hopefully also exhaustive ones, I'll come back to that, then we try to specify our priors. We use our background information, everything we know, to give a guess as to which, going in, before we've seen new evidence, which explanation or theory do we think is going to be a better one of this case or its outcome. Now, if we don't have a lot of prior information, we could just assign equal probabilities to the two explanations. In terms of logarithmic scales, that's giving sort of 0 decibels in favor of either hypothesis, right? We can also do some sensitivity analysis, and we can try out different priors and see how much using different priors ends up with different posteriors, given the same weights of evidence, right? So there are a couple possibilities there. Then we'll get the evidence. We'll treat evidence from different sources as distinctive. We want independent pieces of evidence, right? And then we can aggregate the evidence in different ways. We don't want to get too fine-grained and have, thousands of slightly different pieces of evidence, and we don't want to be too crude. So we're going to have to choose some pragmatic middle ground over what constitutes a piece of evidence that we're going to do on our analysis on. And then we mentally inhabit the world of each of the alternative hypotheses and ask, in that world, if that hypothesis was true, how likely is it that we would find evidence that has this value, right? And we do that for each of the hypotheses, or we can do it for comparing pairs of hypotheses. How likely is it, what's the net weight of evidence or the net likelihood when we consider this one versus this one? Is this one, shouting and this one is whispering that this evidence might be true, and so we'll take a shout minus a whisper, say sort of 60 decibels minus 30, and then the net weight will be 30 decibels in favor of one hypothesis, right? So we also condition the likelihoods on the previously analyzed pieces of evidence. So if we've already updated on one piece of evidence, that's now our new prior going into our analysis of the next piece of evidence, right? This also forces us to think about what is the background information, the sort of implicit information that we're using that's informing our prior. If we have a different prior from somebody else, and they say, well, why did you pick that as your prior? Why do you have so much confidence in this your explanation? And then you'll give the evidence that you're aware of as to why you have that strong confidence. Well, maybe that's evidence they hadn't heard of or thought about, and that may force them now to update their prior already. So since people have different evidence in their personal and intellectual histories, they may start with different priors, but now they can bring that evidence out from the background and try to convince each other about what is the proper prior, right? Okay, finally we simplify by considering the relative ratio or weight of evidence for one hypothesis versus another. All right, so let me work through an example to show you how that would work. And this is from Tasha Fairfield's work. She was looking at tax reforms in Chile, and one particular puzzle, as one part of a larger project, is the puzzle of why the opposition party in Chile agreed to end a regressive tax subsidy. So there was a tax subsidy that was favoring wealthy people, and the opposition party was a party that had more support from wealthy people, and so you would think the wealthy people would want to maintain this tax subsidy, but this opposition party agreed to get rid of the tax subsidy. So that's a little puzzling. Why did they agree to do that? So this is also used in Fairfield and Charman's 2017 article as an example. So let's simplify a bit and just have two alternative explanations. And let's assume that they're mutually exclusive and exhaustive, right? And you could do this again with more hypotheses if you want, but I just want to keep it simple just to illustrate the logic here. So let's assume that they have will give equal priors to each of these hypotheses. So that would be 50-50 if you're using probabilities, or if you're using logarithms, 0 decibels in favor of one hypothesis or the other. Okay, and here's our two hypotheses. One is what Tasha calls the equity appeal. This is the idea that in a presidential candidate's debate, the conservative candidate, who's the opposition candidate, was pushed on television in the spur of the moment to endorse the idea of repealing this regressive tax subsidy in order to improve equality in society. So that's the equity appeal explanation. A second explanation is the decline in assets explanation, that the assets that benefited from this tax subsidy were just declining in value, and so it didn't matter as much to the wealthy people, and therefore it didn't matter as much to the opposition party, so they could easily get rid of it, right? Okay, so those are our hypotheses. Again, we're assuming they're exhaustive and mutually exclusive. Now we'll look to evidence, and I'm just going to use two pieces of evidence for this example. So evidence one is in her interviews, Tasha talked to a finance ministry official from the left-wing party, the ruling party, who says the tax subsidy was a pure transfer of resources to rich people. There was no way to argue differently. It was not possible for the right to oppose the reform after making that argument about inequality. Okay? Now, you might yourself think about, well, does that evidence favor the equity appeal explanation or the declining assets explanation? And here you would think through the logic of those explanations. It's sort of consistent with the equity appeal, right? But also we might be a little suspicious of this evidence because it's evidence given by the liberal party. And so, of course, that's going to be their view or what they want you to believe, right? That the opposite party, the opposition party, is unfair and is only begrudgingly brought to, acknowledge problems with inequality. So we might think it's kind of consistent with the equity appeal, but we're not fully convinced because we might doubt the veracity of the motives of a left party official or finance minister, right? It doesn't fit the declining assets very well, right? But again, it's probably not strong evidence. So we might come up with our own estimate. Does it favor equity appeal by, let's say, 10 decibels, which is a pin drop, or 30, which is a whisper? I think in her own work with Andrew Charman, in this example, they say, well, this is probably 60 decibels for the equity appeal, so pretty strong, they estimate it, 30 for the declining assets. So for the net weight of this evidence, we just take 60 minus 30, or 30 decibels in favor of equity appeal, right? So in other words, it's about the level of a whisper, not really strong evidence in discriminating between these two hypotheses, but something, okay? Now let's do it on the second piece of evidence here. So the second piece of evidence is from a candidate's debate where the right-wing opposition candidate says, inequality continues, there's a chili that grows, but it's for the few, and the great majority has not benefited. And the liberal candidate, sensing an opportunity here, the president, the incumbent, says, oh, well, the infamous Article 57, this regressive tax subsidy, represents a tremendous support for inequality. Instead of just talking about inequality, why don't we agree right here on stage to eliminate this in less than 24 hours? And the opposition party candidate says, that would be fantastic. We're all in favor of equity. Let's do it, right? So E2 is this conversation plus the fact that a Conservative Party deputy says, somebody who works with a right-wing candidate says, our candidate made a commitment and it was a difficult moment. The political decision was made to support what the candidate said. Okay? So now we have to decide if we put on our equity appeal glasses and imagine that world where equity appeal is true. Well, this seems pretty strong evidence for the equity appeal. Very strong, almost maybe smoking gun evidence, right? Does it seem to fit the declining assets? Not very well, okay? So we're probably going to give this pretty strong evidence, pretty strong weight favoring the equity appeal explanation, particularly because it's kind of not very smart politics for a Conservative Party deputy to say, well, we kind of wanted to favor the rich, but we weren't able to because he kind of got caught on camera. That's kind of a somewhat embarrassing admission. And also he says, or he or she, we're not sure, that the political decision was made to support what the candidate said. In other words, there was consideration maybe to not supporting what they said and dumping the candidate because they'd supported getting rid of this subsidy, right? So that's kind of an embarrassing admission on 2 counts. And so we wouldn't expect that unless the equity appeal was true as an explanation. So we would estimate that. We would probably give it a pretty strong relative weight. So in Fairfield's own estimate, this is 70 decibels in favor of equity appeal, barely a pin drop. It's really inconsistent with the declining assets. So the net weight of evidence is 70 minus 10 equals 60 decibels in favor of the equity appeal. Okay, and remember, 70 decibels is a noisy restaurant. This is saying this is very strong evidence for the equity appeal, right? Now, if we just then sum up this evidence, we started with a prior of 0 decibels. We're not favoring one hypothesis or the other. We're giving them an equal likelihood as our prior. The weight of evidence piece of evidence 1 is 60 minus 30, or 30 decibels in favor of equity appeal. The weight of evidence 2 is 70 minus 10, or 60 in favor of equity appeal. So we just add these up, 30 and 60, and now we have 90 decibels in favor of the equity appeal explanation. And remember, 90 decibels is like the noise in a dance club. It's like really strong evidence that we're going to put a lot of confidence that the equity appeal is the proper explanation for why this change in tax policy took place. Okay, so I've skipped over the math a little bit. That's in Tasha Fairfield and Andrew Charman's book, forthcoming book. But I think you can see that the intuitions and the application is actually not that difficult if you just get over the hurdle of thinking in terms of weights of evidence as a decibel scale, and then just inhabit the world of each hypothesis, assign those weights of evidence, and then it's just addition and subtraction, right, to get the net weight of evidence of the collective evidence that will update from our prior to our posterior. So here the prior is 0, the net weight of evidence is 90, and so our posterior is 90 decibels, or very strong evidence in favor of the equity appeal. Okay, so remember that I just did this for 2 hypotheses. We could do it for any number of hypotheses. I did it just for 2 pieces of evidence to keep it simple. We could do it for any number of pieces of evidence. It just gets to be a lot more work when we have lots of hypotheses and lots of pieces of evidence, but that's okay. You can do the work, right? It's not that difficult to do. So remember also that the real work being done here is not the Bayesian math. It's the estimation of the weight of evidence in the first place. How likely is the evidence under this or that explanation? And it's the estimation of the prior. That's what's driving the ultimate outcome. The math, is just translating the information you're giving it, your prior and the evidence, into the posterior, right? So as I said at the outset, the result is only as good as the information going in that's informing your prior, and then the evidence, if the evidence is strong, you can have some strong updating. If it's not, you can't have strong updating, right? Okay, so the limitations of this, as I said, it's only as good as the information going into it. We can represent uncertainty by using upper and lower bound estimates of likelihood ratios and priors. And we can then do a sort of sensitivity analysis, work it through with this prior and see what or that one, see what the outcome is, work it through with the same prior and different likelihood ratios or different weights of evidence and see how much difference that makes. So we can kind of, sometimes if we have really strong evidence, it kind of doesn't matter what our priors were. We'll end up doing a lot of updating. Or if we have really strong priors, it's going to take very powerful evidence to push us off of those priors, right? A sort of Bayesian sensibility is that extraordinary claims require extraordinary evidence. So in other words, again, if our prior is very powerful, it's going to take extraordinarily powerful evidence to move us off of that, right? So remember also that the alternative explanations have to be mutually and exclusive and exhaustive. In principle, we can make them mutually exclusive. It can be a little bit harder in practice to find evidence that discriminates. But there's also this challenge of making them exhaustive, right? We can't guarantee exhaustiveness because exhaustiveness requires that we've thought of all the possible explanations, including the true one is in that mix somewhere. And, we may have left out an explanation because we just haven't thought of it. We don't know what we don't know. So if there's an explanation that we haven't thought of, by definition, we can't factor it into our likelihood ratios, and we could, then be missing the true explanation. Bayesianism is not going to stop you from that mistake. Bayesianism doesn't tell you some godlike knowledge of the proper range of explanations, including the true one. You have to do that yourself as best you can, and you can never be certain that you've got the true explanation among the explanations that you've considered. So this is one reason that we should never be 100% certain with Bayesian updating, or any other method, I would say, for that matter, okay? So we also need to think about potential biases in the sources. As in the tax example, I was discounting the evidence a little bit as to whether it fit or the instrumental purposes of the person giving the evidence, or I was sort of strengthening my estimate of the weight of the evidence if it seemingly went against the instrumental purposes of the person giving me that evidence, right? As I said, Bayesians should never be 100% convinced, right? Okay, so how do we estimate priors? Let me come back to that issue because it's one of the standard questions people have when they first encounter Bayesianism, right? We could have what we call objective priors. If we have lots of previous evidence of lots of previous cases, then we have a well-informed prior. So let's take insurance companies. Insurance companies have millions of data points of previous customers, and they know, they can give a pretty good guess as the likelihood you'll live to this age or that age, depending on whether you smoke or drink alcohol or whatever else, right? So they have lots of information that informs their priors. And most of the textbook examples kind of assume that we have well-informed priors about the prevalence of a disease in a population, and that we also have good likelihood evidence on the true positive and false positive rates of any particular test, right? But in most of our social science examples, we don't have tons of objective evidence on previous cases. So we might have more subjective priors, right? A subjective prior is just based on what I know, my previous information that I've brought to this case. And you could think of it, I would be willing to wager or bet, that this is, the likelihood that this theory is true going in. Now, we could make actual bets, but we'll never know for certain. But you could think of yourself, maybe it helps you to think in terms of making a wager that this is true or not. But that's based on our subjective information. You could see that as a bug, oh, it's subjective. Different people may have different priors. Well, that's true. Or you could see it as a feature. Different people have different priors because they may have different information. And once they realize they have different priors, they can have a conversation that brings out that background information that's informing their priors. And they can share that with the other person. Now maybe the other person is using that as new evidence to update their prior. So it could be considered a bug or a feature of Bayesianism. We could also start with uninformed priors. In the example I just gave you, I just started with an equal likelihood for the equity appeal or the declining assets explanations. So we could do that, or start with 0 decibels in favor of one or the other. That's another way to go here, right? We might also try to crowdsource priors. We know that crowdsourcing in various realms improves. Crowds make better predictions or estimates sometimes than individuals do. And so one area, and I've been talking with Tasha Fairfield about doing some experiments on this, one area of possible research is to see if in some sense people do better at estimating priors and likelihoods if they crowdsource it, if they have a conversation about why they think the likelihood should be this or that, right? There's some work by Philip Tetlock in his book Super Forecasters, where he shows that groups that are trained in Bayesianism and that share information are better at forecasting events. And there's some other interesting work by Barbara Buffani and I forget the first name of Stedman Bryce, sort of along this line. So there's some suggestive things, but I think we need to do some more experiments and research here about whether crowdsourcing in some sense improves priors and likelihoods, right? Okay, so what's the value added of formal Bayesianism? Well, Bayesianism leverages our prior information, and it uses our understanding of theories, and it uses new evidence to reach new estimates of the relative likelihood that different theories or explanations are true. As I said, if people start with different priors, they may be able to narrow their disagreement, even if they don't fully agree on the relative likelihoods of evidence. As long as they can agree that the likelihoods of evidence point in one direction or the other, they will narrow their disagreement from their disagreement over the prior to a narrower disagreement over the posterior, right? We can also work backwards. If somebody says, this evidence totally convinced me that this is the right explanation, and you could say, well, how confident are you? And they say, well, I'm 90% confident. And you say, well, how confident were you before? And they say, well, I only thought it was 10% likely that was the right explanation before. And you can work it backwards. You can say, okay, if you went from 10% to 90%, then you have to be, convinced that this piece of evidence is 10,000 times more likely if that theory is true than if some other theory is true. Do you think that's actually 10,000 times more likely? And if they say no, well, then you can say, well, you're being inconsistent, right? It's just math. So if you give me, an equation and some unknowns, if you give me the posterior and the prior, I can figure out what the likelihood ratio had to be for you to do the updating in that way, right? Usually we're starting with the prior and the likelihood of evidence and working to the posterior, but if you give me the posterior and the prior, I can tell what had to be in the middle, what had to be your maybe implicit estimate of the likelihood ratio. And if you don't agree with the math, then there's some asymmetry in your own thinking that you're going to need to explore, right? I would say also, even if you don't do the full formal Bayesianism, just knowing how the logic works and using it informally will hopefully improve your traditional process tracing, will make things a little more transparent, will help you to sort of preempt some potential cognitive biases, right? Okay, so what are some implications? As I said, in some ways Bayesianism is intuitive, in other ways it can lead to some counterintuitive implications. So one of these is that evidence that's consistent with a theory may actually make it less likely that that theory is true, right? And usually that would only happen in your subjective experience if there was some other theory you hadn't thought of that fits the evidence better. So you've probably had the experience where you're maybe in a foreign country or different setting and you see somebody doing a certain behavior and you talk to your friend who knows the culture very well and you say, oh, they're doing that, they must have this intention. And your friend says, no, actually that behavior means that intention is less likely because this is the reason for that behavior. So here's an explanation you hadn't thought of that fits the evidence better than the one you did think of, right? Let me give you a real world example here. During the Cuban Missile Crisis, Kennedy was shown spy plane photographs of the fighter airplanes on Cuban runways. And Kennedy looked at those photographs and said, oh, this is terrible. The way those planes are lined up on runways, it looks like they're planning to launch them very quickly and do some airstrikes against United States military bases in the southern United States. Now, fortunately, there's some Air Force people in the room who are used to interpreting these photographs and know a lot more about air operations. And they said, no, Mr. President, that's the way you line planes on a runway when you're not planning to launch them quickly. And you line them up that way because you want to make sure that if one catches fire and explodes, it doesn't, start all the other ones on fire. And when you really want to launch the planes quickly, you line them up this way. You take a higher risk that all of them will explode at the same time, but you make it more possible to get off the runway quickly. So here Kennedy thought, the evidence was consistent with his explanation. It was actually more consistent with the explanation that he had not thought of, right? Second, Bayesianism gives a logical rationale for why independent evidence is good, right? Let me give you an example here. if we're looking at photographs to try to determine if an object that's being photographed is a real duck or a wooden duck that might be used by a hunter as a decoy. Well, if we look at kind of blurry photographs from different angles, at some point it's not helping us very much. It's all the same kind of evidence, right? It's not independent evidence anymore. If it looks like a duck from a distance without a photograph, if it walks like a duck, if it sounds like a duck, if you're not a vegetarian, if it tastes like a duck, these are independent kinds of evidence that can still update the likelihood that it's a duck versus a decoy, right? So in Bayesianism, once you've looked at a certain kind of evidence over and over, it becomes less likely that the next piece of that kind of evidence is going to really change your view, right? Whereas if there's some different kind of evidence that's independent, and you haven't looked at it yet, there's still more of a chance that that will change your view about which explanation is a powerful explanation of the outcome of a case, okay? So, third implication is if you have lots of weak pieces of evidence, but they all point in the same direction, that can result in strong updating. So in a court of law, we might call this circumstantial evidence, right? If a lot of circumstantial evidence points in the same direction, then we'll say, well, it becomes increasingly likely that this person is the guilty party, right? Okay. It also helps us think about when absence of evidence is evidence of absence. Now, that was a phrase in philosophy of science. It was made then more famous when our Secretary of Defense, Donald Rumsfeld, during the invasion of Iraq in 2003, early on he said, well, the fact that we haven't yet discovered weapons of mass destruction doesn't mean there weren't any weapons of mass destruction. And it wasn't a terribly unreasonable thing when he said it, because we had just taken control of the country. We hadn't been able to look all over the country. A few months later, after we'd looked all over the country and we still hadn't found weapons of mass destruction, well, now absence of evidence is evidence of absence, right? So whether not finding evidence is telling us something depends on several things. What's the likelihood that the process happened in the first place and generated evidence? What's the likelihood that the evidence will still be around? What's the likelihood that people will make the evidence available to us or that we will access it? And how hard did we try to look in the right places to find the evidence? If it's plausible that that process would leave behind evidence that we could access and we've looked hard in all the right places and it's not there, then we'll say it's evidence of absence. But if those things aren't true, if it might not have been kept or made available to us, or we haven't looked in the right place or haven't been able to, then we can't say that absence of evidence is evidence of absence, right? Okay, so there's some differences and limits here. As I said, between process tracing and Bayesianism, we should never be 100% confident because there might be some other explanation we've not thought of. Process tracing in the social sciences has more of a theory generating aspect to it than most discussions of Bayesianism. We may inductively see a piece of evidence and then come up with a new theory. You can still give a Bayesian reading of that. That new evidence still may have a likelihood relative to the new theory and relative to the alternative explanations you've already thought of. Fairfield and Charman talk about this as well. So once we come up with the evidence and generate the idea, then we can still give it a Bayesian reading, but that generating the idea is kind of a creative human process that's not really sort of Bayesian. Also, when a lot of discussions of Bayesianism in the medical sciences don't have to deal as much with the possibility that patients are misrepresenting, their symptoms, right? They might if they're embarrassed about, a sexually transmitted disease or something, but we have to worry a lot more in social science examples that witnesses or interviewees, either intentionally or unintentionally, are presenting information in a way that's favorable to themselves, right? They may have inadequate recall, they may be intentionally putting a spin on things and so on. So we have to think a lot more about evidentiary biases than, say, in some of the medical sciences. Okay, let me conclude then, and I'll introduce an exercise. So there are costs to going formal and Bayesian. It can take a lot more work, and it can take a lot to write up, and it can become very tedious to read. when Tasha Fairfield wrote up her initial case study of the tax case that I gave an example earlier, it was 1,300 words. When they wrote it up as a formal Bayesian analysis, it was 10,000 words. So, 7 times as long. And this was just one case, and her book had 33 cases. So to have gone full formal Bayesian on all of those cases, on all the pieces of evidence, would have been impractical, would not have been possible. There's also a danger that used badly, Bayesianism will create a false sense of confidence or precision. We could counteract that by doing some sensitivity analysis, as I discussed earlier. And I would say on the plus side, Bayesianism can prevent certain inferential errors. Being explicit clarifies our claims about priors and likelihoods, and it clarifies where we disagree with other people. Do we disagree over the prior? Do we disagree over the likelihood of evidence if the theory is true? Or do we disagree on the reading of the evidence itself? I think that person I interviewed told me the truth. You think they're a shameless liar. We're going to update differently on that evidence. But we can find out where it is that we disagree and why we're updating differently, right? So a strong argument here is that Bayesianism makes explicit the kinds of calculations you had to be doing anyway and doing informally to make claims about case outcomes based on evidence. So it's just forcing us to be explicit at what we were doing implicitly. So I would say it often makes sense to do some Bayesian calculations on a few pieces of what you consider to be the most powerful evidence. Maybe it goes into an appendix, or maybe a footnote, maybe it goes into the main text, right? Even if you're not doing full Bayesian on all of the evidence, often in our research, it's just a few pieces of a big body of evidence that make us strongly convinced. It may be a lot of other smaller pieces of evidence that we'll introduce in our narrative without going into full formal Bayesian analysis. Okay, this is also Fairfield and Charman's take on the pros and cons, the advantages of Bayesian analysis. It largely tracks my own. In the interest of keeping this short, I'm just going to move ahead, but you might want to pause and read through those if you want. Okay, let me set up an exercise then. If you're taking a class with me, you can work through this and then we'll talk it through. If you're doing this on your own, there's a link here where you can get to the exercise. But let me just introduce the background so that you're able to do the exercise. So this is building on work by Kenneth Schultz. He's got a book, Democracy and Coercive Diplomacy, and he does a case study on the Fashoda crisis. And I did an earlier analysis of this, and then Tasha Fairfield and Andrew Charman have done a more full formal Bayesian analysis of Schultz's work on the Fashoda crisis. So let me give you the background here. In 1898, the French and the British were sending expeditionary forces up the Nile River, and they arrived at the headwaters of the Nile River. And in international law, then and now, whoever controls the upper reaches of a river have a lot of downriver rights. So both the French and British wanted to claim this territory as part of their empires, and they were confronting each other over their respective claims to control this territory. Now, at the time, both France and Britain had democratic institutions. And also at the time, it was generally agreed that Britain had a far superior military, especially its navy. And it was generally understood that if France and Britain got into a war over the Fashoda territory, that nobody would be coming to help out France. So let's just posit these as, generally understood, not disagreed upon background facts, okay? So the crisis ended without a war, but there are alternative explanations for that outcome. One is the balance of power argument, that because Britain was so much more powerful than France in terms of its navy in particular, that it was sort of obvious that Britain was going to win if there was a war, so France ended up conceding, and indeed France did concede. So that would be one explanation, one hypothesis. Another has to do with democratic values, that in democracies, another democracy has some presumptive legitimacy, so there's a higher bar to go to war with another democracy, so you'd be reluctant, you wouldn't be champing at the bit and eager to go to fight against another democracy. Another one has to do with democratic institutions, that these politically constrained democracies make them less warlike, especially vis-a-vis other democracies, that voters might vote out a party that's too hawkish, too eager to go to war. And then a fourth explanation, and this is the one that Schultz is the most interested in, is that the resolution of this crisis has to do not just with relative power, but with the credibility of signals about the willingness to use military power to fight over fasciotum. And the way this works is that when a democratic leader, in this case the British Prime Minister and Foreign Minister, make a threat to use force, if the British opposition party in Parliament says, we agree on that, we're willing to fight over this, well, that makes it a very credible threat to the French. Whereas if the opposition party in Britain says, we're not willing to fight over this, that would undermine the credibility of that threat, and the British might have to back down because it's been revealed that they have a bluff. Okay? So those are our four alternative explanations. Let's assume that they're exhaustive and mutually exclusive. You could challenge that assumption, put in some different explanations. I just want to work the exercise and show, given these assumptions, how might we weight the evidence. Okay? So we want to estimate the relative weight of the evidence for each pair of hypotheses, right? And ask, if this hypothesis was true, how likely is that evidence relative to how likely is that evidence if this other hypothesis is true, right? So keep in mind this decibel scale. 10 decibels is a pin drop, 30 is a whisper, 60 is a conversation, 70 is a noisy restaurant, and so on, right? So I'm going to give you pairs of hypotheses. If the weight of evidence favors the first in that pair, then you'll report it is a positive weight of evidence value in terms of decibels. If the weight of evidence favors the second hypothesis in the pair, you'll report it as negative. So let's look here. We're comparing the credibility of threat hypothesis versus the balance of power hypothesis. If we think a piece of evidence E1 favors the first, we'll report it as positive. And in this case, if we think it favors it by 40 decibels, that's what we will report. Okay? So if we thought this evidence E1 favored the balance of power, we might say, negative 10 or negative 20 or negative 30 or 40 decibels, right? So that's simply how I'm asking you to report your estimates, right? So let's take a specific example here that's the first piece of evidence in the exercise. And this is evidence E1. The evidence is that the crisis lasts for several months. So now we have to say, given the crisis lasted several months, how likely is that under these alternative hypotheses, right? So for the credible threat hypothesis, it's pretty likely that the crisis is going to last a while because it's not until the signals are revealed, and it's not until the Parliament opposition party comes to a view on this that the threat becomes credible, and then it will be acted upon by the French on the other side, right? Whereas for the balance of power hypothesis, if that's what's driving the outcome, that should be obvious from the very first day. And so if it's obvious that Britain is going to win in the end, then the French should concede on the very first day, because why raise this to a crisis and then have to back down in some embarrassing way? So, and this is from Fairfield's estimate of this example, Fairfield and Charman's estimate. They suggest that this piece of evidence favors credibility threat over balance of power by 40 decibels. It's pretty strong because it's unlikely to last several months if balance of power is the true explanation. It is likely to last several months if the credibility threat is true, right? Similarly, for credibility threat relative to democratic values, well, it's not likely to last several months if it's democratic values. We shouldn't have a crisis. It should just be calm diplomacy. Maybe we'll divide it up some way or something, right? So this favors credibility threat over democratic values. And similarly, democratic institutions, very similar to the logic here, we wouldn't expect a several months crisis if democratic institutions are the proper explanation of the outcome, right? So I've worked it out for you and given you, in fact, Fairfield and Charman's estimates of the weights of this piece of evidence for each pairwise comparison of the hypotheses. What I want you to do for the exercise is to work through the other pieces of evidence in the same way and to come up with your own estimates of the weights of the evidence, right? And then you can add them all up at the end. So that's what I would like you to do in the exercise. This is a link to the other pieces of evidence so you can go through that exercise. When we come together as a class, if you're taking class with me, either as a whole class or maybe I'll break you out in groups where we'll go through this exercise again, but in the group you'll give your own estimates and you'll justify those, and you'll listen to the way other people justify those, and you may be able to adjust your estimates, and then we'll come back as a class and see where we are and how we've thought through this exercise. Okay, so either on your own or if you're taking a class, take a look at that document, work through the exercise, and then if you're taking the class with me, we'll go over it in class.